Okay, for number 3, some more practice using this last topic, the Lagrange error bound. We've got a function, and we'd like to make a Taylor polynomial degree 3. Notice where we're centered. We're centered at -8. You know, sometimes you'll see teachers do this too. They might go ahead and build themselves a little bit of a table. And they might say, look, here's your n, and this would be the nth derivative evaluated at x. And you don't have to write it out this way, but I think a lot of kids just like that orderly fashion. Just wanted to show you another way you could do it. You could say, well, what if we were taking the 0th derivative? 0th derivative is really just this thing right here. It's the cube root of x. That's x to the 1/3. Of course, if you plug -8 in, what's the cube root of -8? Well, it's -2. Then what? We could say, well, let's take our first derivative. Well, you'd get 1/3 x to the -2/3. If you were to plug an 8 in, remember this right here, you're going to take the cube root of -8, I should say, and you're going to really have this as 1/3 x to the 2/3. So you're going to take that cube root of -8, you get -2, but then you square it, you get a 4. 4 times 3 is 12. You'd get 1/12. If you were to take the second derivative, well, you bring down a -2/3, you'd get -2/9. And then you'd subtract a 1 from your power, subtract 3/3, you get -5/3. Again, if you were to plug in a -8, again, what are you really seeing? You're seeing that you've got -2/9 x to the 5/3. We already know the cube root of -8 is -2, but -2 to the 5th power, well, you'd get -32, and you can cancel out that -2 up on top. You get 1/16. 1/16 times 9, 1/9 would be 1/144. Could work that out pretty quickly. Here, taking your next derivative, you could get 10/27. You bring down that -5/3 and you multiply that out, and you'd get x to the -8/3. Well, of course, right now things are getting quite a bit more complicated. Don't get me wrong, you could have been doing this all along. You could have said 10/27, and then you'd multiply where we have -8. Well, probably want to put that in parentheses, -8, and then we're going to raise that up to the -8/3 power. And of course, you're going to get some decimal right there, but if you work that out, you can see you'd get 5/3,456. So you could have worked that out by hand just as well. But here are your first 3 derivatives. You could say, hey, let's stop there. We are only going to a 3rd degree polynomial. But remember, with the Lagrange error bound, you have to go one step beyond. We're going to take our next derivative, bring down -8/3. Hopefully you could see you'd get -80/81 x to the -11/3. We're not going to plug in -8 into that Lagrange error bound. We're plugging in a z instead, and we'll be getting to that shortly. But let's just review how we find a 3rd degree Taylor polynomial. We're centered at -8, so we'll have f of -8 plus the first derivative at -8 times x plus 8. This is x minus -8. It turns into an x plus 8 to the first power all over 1 factorial. We'll have our second derivative evaluated at -8. But now this is x minus -8. It's x plus 8 to the second all over 2 factorial. One more. We'll take our third derivative at -8. And we're going to multiply by x plus 8 to the third all over a 3 factorial. And if you were to clean this all up, if you were to just clean this all up real fast, f of -8, we already said, hey, that's -2. F prime, that first derivative, that's your 1/12. and dividing by 1, that's going to be fine. The second derivative right here, that's going to be 1 over 144. But then you're going to divide by 2. So that's multiplying by half. That's 1 over 288, x plus 8 to the second. Here we've got this 5 over 3,456, but we're dividing by 3 factorial. That's like multiplying by 1 over 6. So let's see if we multiply that all out. What's that? 20,736, I believe. Yeah, pretty sure that's right. We'd have x plus 8. Let's double check that. Yeah, okay, so that's your third degree Taylor polynomial. Well, you should also talk about your error, your R3. Well, what is that exactly? That's your fourth derivative evaluated at z. And then you'd have x plus 8 to the fourth power, and then you're going to divide by 4 factorial. Wow. Well, as we clean that up, I think you could see that we'll have a negative 80 over 81 dividing by 24. And you can see real quickly if we took negative 80 all over 81, and then if we just divide that by 4 factorial also, well, we're going to get, this value right here. If we did math frac, you can see we'd get negative 10 over 243. We could do that by hand just as well, of course. But then what? We also have this x to the negative 11th, but we're plugging in z to the negative 11th. Negative 11 over 3, pardon me. Then we've got x plus 8 to the 4th. One additional little thing, z is between x and 8, and negative 8, pardon me. Wherever we are evaluating is x, we are centered at negative 8, so the z value is always between those two. So right now, they're asking us to estimate our error. And, they also want us to estimate what the cube root of negative 8.5 is. So if we did p sub 3 of negative 8.5, we'd have to just type this all out in here and get a quick estimate. This is just some number crunching. So, we'd take negative 2 plus, and we can do math. Alpha y equals, get a fraction going, and we'll get 1 over 12. And then we'll have negative 8.5 plus 8. And then we'd say plus, well, now we'd want to go alpha y equals 1 over 288. But then what? We're going to have negative 8.5 plus 8, but this time we're bumping it up to the second power. And then we could say plus alpha y equals, this is where our fraction gets quite a bit uglier, 5 all over 20,736. And then we'd have our negative 8.5 plus 8, but we're raising that up to the third power. And if we just work this all out, you could see that we're getting an estimate of roughly about negative 2.0408. So, not so bad. I do want to also point out to you that if we would have taken our calculator, this is always a point of interest, if we would have said, well, what exactly is our cube root of this thing? You can see we're actually remarkably close. We're doing pretty good. Well, the big question is, what would the Lagrange error bound say that our error is? Well, our error, and we're going to go right from here, this simplified form right here, for our Lagrange error bound, our error in absolute value has to be less than R3 of negative 8.5. So that is the square, the absolute value of negative 10 all over 243. I'm going to bring that z to the 11/3 down. And then we'll have negative 8.5 plus 8, and we're raising it up to the 4th. But z is between negative 8.5 and negative 8. Now, at this point, the big question is, since I don't know what z is exactly, what can we do here to maximize this error? And I'm actually going to write this down. To maximize the error, we're going to make a choice between these two values of z. Z is in the denominator. And guys, the smaller your denominator is, the larger your fraction is. So I'm going to choose z to equal negative 8. So the denominator is as small as possible. So what you're going to see is in absolute value. By the way, sometimes kids will point out negative 8.5 is actually smaller than negative 8 is a point that kids will point out. But please remember, this is all measured in absolute value. So what I'm getting at is actually this. If you were to just look at what's happening in absolute value, you'd see that the negatives get absorbed, and actually you'd still want to be choosing that to be negative 8. What you can do real quickly then is see that your error, you were to just work this thing out on the calculator, and negative 8.5 plus 4 is really just a negative 0.5 to the 4th. If you to work this thing out, you could find your error bound. So we can do that real quickly. Let's go ahead and just get alpha y equals. And, we can even ignore negatives altogether. I didn't put an absolute value down here. Certainly we could. Look, if we put in a negative 8 and then raise that up to the 11/3, then what? I'm going to come over here and say multiply that to a negative 0.5 up to the 4th power. If you were to work this thing out, you get something very, very small. You get 1.255 times 10 to the negative 6. So your error is less than 1.255 times 10 to the negative 6.